Some of this is going to really take us back to grade 10. So much of the math that we do starts in grade 10. Such an important year. And there's nothing new about this first little piece. When two lines exist in two space, there are three possibilities. What are they? Somebody give me one of them. John? They never touch. What would that look like? Yeah, so I could have two lines, or I could have more, of course, that are parallel and distinct. We specify this, they're parallel and distinct. So there's no solutions. What else? Mason. Good. So one solution. They cross at a point. And the last one. Jason? Yeah, they cross at every point, or they. This is a strange one, but we call they're parallel and coinciding, or parallel and coincident. So I've got one point or one line, and then the other line right on top of it. This one's a tricky one because so parallel and coinciding. So infinite solutions. I don't know. This one always kind of rubs me the wrong way because it's the same line. It's the same line. I mean, I don't know. Is it in a real world application? It's two people who have walked along the same path or something, so they're different people. I don't know, but it's the same line. One's probably just in the new terminology a scalar multiple of the other, right? So, but they're the same line. Their equations look slightly different. But anyway, but you could have two lines that turn out to be the same line, and so they touch everywhere. There are infinite solutions to that linear system. Or you can have no solutions if they're parallel and distinct, or you can have one solution. We've talked a lot in the past unit about lines and now planes being parallel. And we can see how important it is, and you probably saw before, but how important it is to determine, are they parallel and distinct or parallel and coinciding? Those are two very different situations when the point of intersection of a linear system, as we saw back in grade 10, is the solution to some kind of problem. Like the coins questions, or when one car catches another car, or two cars, their paths meet, or something along those lines, right? There's all those different actual real life problems that can be solved that turn out to be linear systems. And then now we've seen, extending that when we have a quadratic and linear system. Well, you can have because you can have one solution or two solutions or all kinds of things. And so we know that this is just linear. These are straight lines. That keeps it relatively simple. If we extend it to other polynomials, we get more, but there's patterns in those possibilities as well. Any questions about that? It's pretty straightforward. Okay, let's try one. Investigate the intersection of the following pair of lines. So what's different now in grade 12 compared to grade 10 is in grade 10, we only really had one type of equation. Sure, it could be in standard form, or it could be in slope-intercept form, y equals mx plus b. But all of those are kind of polynomial form. And now we have different forms. We have scalar form, or we have parametric or symmetric. And so the math looks a little bit different, but the idea is the same. Two lines, L1 and L2. When will they cross? John? When they equal each other. When the x from L1 equals the x from L2 and the y from L1 equals the y from L2. So these are going to equal each other when x equals x and when y equals y. But how do I figure that out? Well, interestingly, like I've got 4 unknowns here. X and y and t and m. But when I set it up for x equal x, I get 2 plus t equals 1 minus 2m. That's when x equals x. And when y equals y, I get negative 9 plus 4t equals 9 plus 3m. And now I've got 2 equations with 2 variables. And so this is a different linear system in a way. But when I solve this, I'll find the values of t and m that make the values of x and y true. If you overthink this, it might feel like it shouldn't work or it's strange that it works because I've got 4 unknowns but I've actually got 4 equations, so I guess we've got enough information to make it work. Okay, so you just set x is equal to x's, y is equal to y's, and then solve it like a linear system. So what I'm going to do is I'm going to solve equation 1. So moving the 2 to the other side, I get negative 1 minus 2m. And then I'm going to sub 3 into 2. Do we need reminders of all the little tricks and details of this stuff? Like you can't sub 3 back into 1 because 3 came from 1, right? That's not going to solve the system properly. So let's see, negative 9 plus 4 times negative 1 minus 2m. And then I'm going to solve this. And I got m is negative 2. Everybody happy enough with that? It must be right because it worked out to a whole number. If I made a mistake, it would probably give me a decimal, right? That's a nice little check in these. Not necessarily, you're probably going to get some decimal answers, but everybody okay with this so far? So what do I do next? In grade 10, we'd go and find t. Should we do that? What are we ultimately trying to do? Do I need both m and t? That would be an interesting check. You don't need to do it formally, but that would be an interesting check, and it would be easy to find t if you just went in here, and then you could, mentally or on your calculator sub into t, sure, and make sure you get the right values. But if you've done everything right, all we need is m in this case. So I'm going to do m, or I'm going to call this equation 4, and then I'm going to go 4. I don't actually have to say this, but into L2. I'm just kind of describing what I'm doing for the lesson. So therefore, x equals 1 minus 2 times, what was m? Negative 2, yep. Which equals 5. And y equals 9 plus 3 times negative 2. So that's 3. The solution is 5, 3. Everybody good with that? Pretty straightforward. Quick heads up. If we were solving for m and we got 0m equals some constant like k, Again, if you remember back from grade 10, this is not possible. This is where like k doesn't equal 0. So k is anything other than 0. 0m equals 5. That's not true. That's never true. So these are this is no solution. They're parallel and distinct. And if we got something like 0m equals 0 or 0t equals 0, obviously whatever the variable is, this is infinite solutions. So a lot of what we're going to be thinking about is what is the algebraic solution, interpreting it, what does it look like in the different cases? Okay. It feels to me like back in grade 10, our purpose was to find the point of intersection. That's what we were really focusing on. I mean, we were brushing up our algebraic skills. It's an important thing to be able to solve a linear system, but you do little linear systems after that unit in grade 10, all throughout grade 10, grade 11, and MHF without sometime knowing it, but often we are looking for the values of A and B or whatever, right? And it ends up being a linear system. So we're good at finding that. I feel like now it's really more about, we're more interested in the nature of the system. Sure, if there's a single point where they cross, we're going to go ahead and find it. But more of my thinking is about how the algebra shows, the nature of this system and how does this system interact. Maybe I don't even care about the point. I just want to know, is it going to meet at a point? And if not, why not, or that kind of thing. Okay, so, interesting question. Determine the number of solutions to the system without solving. And what do we notice about this system? John? Yeah, okay, so we're going to get to that. But in general, we're given this in vector form. So in vector form, the math all looks a little bit different. Depending on the form you're given, you might solve this kind of a question in a different way, but in vector form, what would the vectors be like under the different circumstances? One solution, no solution, infinite solutions. Do you see where I'm going with this? This touches on what John was just saying. Like, without solving, how can I tell which of the three situations we're in? So this is how we reflect more on the nature of the system and the properties of the equations and that sort of thing than actually finding the solution. Elif, do you have something to say? It does. If they're scalar multiples, they're parallel. So if they're not scalar multiples, what does that mean? John? Perpendicular would be, okay, so just to clarify, the first thing John said is exactly right. Scalar multiple could be a different direction. And so they're still parallel even though they're opposite directions, or collinear, right? So I think if they are not scalar multiples, they meet at one point. That's it. We're done. Whether it's perpendicular or not, I don't know, but we don't necessarily even need to know that. I mean, maybe we do. Who knows what we're doing? But, right, to answer this question, if they are not scalar multiples of each other, you're done. They cross at a point. Think about that. If you don't believe that, or if you're not sure, convince yourself that that's true. Visualize it. Two vectors that are not collinear, the direction vectors are not collinear. Those lines will meet somewhere eventually. Okay? But in this case, direction vector 2 is equal to 2 times direction vector 1. Therefore, the lines are parallel. So they're either going to be coincident or distinct. We don't know that part yet. Again, go back and think about what a direction vector tells you. A direction vector doesn't exist in a single location in space. The direction vectors all start at the origin. We're in 2 space right now, but those direction vectors are pointing the same direction. One starts at one point, the other one starts at a different point. That's what the position vector tells us. We call it a vector because otherwise we couldn't do any math with it, but really it's a point. So what do we do next? What do you mean by that? Yeah. They will, but under what terms? They won't be scalar multiples of each other necessarily. So we can't just look at them directly. Yeah. So if you start at one of the points and use the direction vector, will you eventually end up on the other point? That's very good thinking. But the easier way to think about this is, why don't we take one of those points and check it in the other equation and see if it works out? Because if one of the points is on the other, if this point is on the other line, which, John, we'll check what you're saying. If I use this direction vector on this point, will I eventually get here? Right? How do we do that? By checking if the point's on the line. Go ahead. You're doing the math that we're going to do in your head and solving, yeah, by inspection. Very good. Yeah. So what's your prediction here? What's your thinking? Okay, good. But let's do this formally. So we're going to check. I'm going to check 5 in L2, which is not actually called L2, but the second one. And the check for these looks a little bit different. So I'm going to say 1, that's x, equals -5 minus 6s. And 5 equals 19 plus 14s. 6 equals -6s. S equals -1. -14 equals 14s. S equals -1. S is consistent. Therefore, 1, 5 is on L2. Therefore, the lines are coincident. When we say they're coincident, we're saying that they're parallel and coincident. That includes the idea of parallel. So we don't have to say. But we do. I think it said determine the number of solutions, which I haven't explicitly stated. So lines are coincident, and there are infinite solutions. Happy with that? Nothing too groundbreaking there. I don't think. But here's where it gets more interesting. If we consider two lines in 3 space, we only get one more possibility. I think that's interesting. So we still have the one solution. They could certainly still both be the same line. They could be coincident. I know these are lame lines, but my rulers are my lines. And they literally exist in 3 space. Like, this is perfect, right? So, one solution, they cross at a point. I mean, they can't not be true. I'm doing it right now. Infinite solutions, they're coincident. They're the same line. They touch each other everywhere. Could 2 lines in 3 space be parallel and distinct? Well, let's test. You can make your hypothesis. Yep, looks like they can because I'm doing it right now. That's my proof. So no solutions. What's the 4th? What would that look like? Yeah, very good. You guys are ahead of the game. Done. Right? These lines will never touch each other. Right? So once you can pull them apart into different planes like that, you've got straight lines, but they won't cross. We call this skew. And it makes things a bit more interesting because when we're determining the nature of the system, the direction vectors, the all these things will not like the fact that they're parallel or not isn't the only case. There's other things going on. Okay, so let's take a look at a few examples. We've got a bunch. We'll get through as many as we can. Oh, we got 30 minutes. We'll probably be fine. Again, it has a bit of a different flavor to it depending on the form that you're given. So here we have a parametric and a vector form. And we see that this is 3 space because I've got an x, y, and a z. And each of these have 3 coordinates. So that 3 space says x, y, z. So what I'm going to do for this one is I'm going to take L1 and put it in vector form. So 3, 2, 28. -1, -1, 1. So direction vector 1 is -1, -1, 1. Direction vector 2 is 2, -4, 5. So the direction vectors are not parallel. If I have them both in vector form, I can see that from the beginning. So it's a good first step. How are we going to proceed? Direction vectors will still tell me if the lines are parallel or not. Even if the lines are skew, their direction vectors don't exist in a particular position. So if I think about their direction vectors on those lines, but then start them at the origin, I mean, they'll still be either parallel or not. So that all works fine. So what can I do from here? Anybody have an idea? It's not unlike what we did previously. I can solve, so if the direction vectors are not parallel, the lines will pass over, under, whatever that means, but each other somewhere. At that point, let's say their x and y are equal. So I can solve this system for the x and y where that occurs. And then if that's consistent with the z, or the third coordinate, whatever, then the lines actually meet at a point. So what we're going to do is we're going to do the same thing we did before. We're going to solve for x and y and check it with z. And if it checks out, if it's consistent, then sure enough we have a point of intersection and they cross. But we will find a solution for the x and y, guaranteed, because they're skewed. So there will be some place where the x's and y's alone cross. It's just whether or not is that also consistent with the z at that same position. Okay, so we are going to do x here first. And so I'm looking at the two equations, and I get, for the x parts, it's 3 minus t. That's useful when it's in parametric, equals 7 plus 2m. So I'm kind of turning the vector form of L2 into parametric form in my head. And I'm going to solve this for t, because it's going to make my life easy. If it's not easy to solve for t, you may or may not do this step, but in this case it can. So it works out to negative 4 minus 2m. And I'm going to call that equation 1. Negative 10 plus 4m. All of these I can solve for t. You could set these three up and see which two you like best. Which two are easiest? It doesn't have to be x and y and then sub into z, of course. Negative 11 plus 5m. So I'm going to solve the x and y. I'm going to solve equations 1 and 2 and check it in 3. In this case, we do need t because we've got to sub both of them in. So I'm going to check 1, -6, which is mt. There's not really a standard for that, right? But that's m and t in equation 3. And because we have lots of different equations and lots of different things going on, it is super important that you are clear. I mean, you don't have to use the exact notation that I'm using, but you should be communicating what you're doing. Like you could just say check in 3. You don't have to necessarily state the point. And when we do a check, we do left side, right side. So left side equals t. Right side equals -11 plus 5m. T is -6. -11 plus 5 times 1, which is -6. Left side equals right side. Therefore, the lines cross at a point. We good with that? If I want to know what the point is, which we do, I can just take t, maybe sub it into parametric form up here at the top. Super easy to find the x, the y, and the z value. So at t equals 6, isn't that right? -6. -3 minus -6, which is 9. Y is 2 minus -6, which is 8. And Z is 28 plus T, so -6, which is 22. Questions or comments? So far, straightforward. What we've done is relatively consistent from 2-space to 3-space. A little bit of extra work, a little bit more going on, but it feels familiar. Okay, let's try another one. I'm not sure we've done this explicitly like this. Oh, well, if you look back at the original note, throughout the note, this is all written out, but we never wrote it, I don't think, all together. So I think it's important that we now start to look at this relationship so that we don't have to do the conversion every single time. And we see where the direction vector is from vector form, from parametric form, from symmetric form, where the position vector is in each form. So we can pull that out without rearranging. Save us some work. So direction vector 1 is 1, 3, 7. What's direction vector 2? Nice, 5, negative 5, and 2. So it's just the denominators. And what do we notice about that? D1, sorry, yeah, does not equal K times D2. Therefore, they are not parallel. Everybody okay? So I'm going to take L2 and put it in a better form to solve this system like we did previously. You could pick. Vector form would be fine. Parametric form is actually our favorite probably for this because that's where it's already x equals, y equals, z equals. And it's easy, probably, well, I don't know, it's probably the same, but easy enough to go to parametric form. So I'm going to do that. This is good practice for these guys over on the side. Taking symmetric, it's x minus x0. So if it's x minus 3, x0 is 3, positive 3. Careful of that. That's something we're used to in lots of different places, but that would be an easy thing to mix up. So this one's negative 3 minus 5m. And this one's a bit tricky, so take a look up here. It's 4 minus z. That's kind of backwards. So I'm going to get negative bracket z minus 4 over 2. But then that negative is actually going to go, so z minus 4 over negative 2. When I kind of pull that apart and put it in the right form, you have to do that for sure. If you were to just solve it for z, you'd get that same thing, right? So, so that makes z 4 minus 2m. Now go ahead, you set x is equal to x's, y is equal to y, z is equal to z's. If you want to get started on that, try to beat me, go for it. Solve this how you like. If you prefer elimination, you can do that. I'm going to sub 1 into 2. -19/20, -19/20. I'm going to sub that back into 1 to find t. And you get a quarter, I believe. Somebody wants to check that? We good? Last step. Check in our third equation, right? I think this works out to 59/10. When the x's and y's of the two lines match, the z does not. Therefore, the lines are skewed. Left side does not equal right side. Therefore, lines are skewed. You okay with that? Any questions? Try one more. I'm going to let you get started on it. What do you notice? Anything? Nice. So direction vector 1, m is 1, 1, 1. And direction vector 2, -2t, 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 -2, -2, -2. So d2 equals -2 times d1. Therefore, John? Yeah. Therefore, L1 is parallel to L2. So now we just want to decide what kind of parallel system this is. Do you remember how we did that before? Again, it comes down to getting familiar with these forms and what information you're given, although we kind of saw right here that we are, in a different way, we are given always a position vector and a direction vector. So what can I do with that? What did we do last time? We checked if a point from one was on the other. Position vector is a point, so we can do that. So we're going to check if, what is the point? 1, 2, negative 4 is on L2. So I'll check the x first. 1 equals 2 minus 2t. Negative 1 equals negative 2t. T equals a half. So far, so good. Since t is not consistent, (1, 2, negative 4 is not on L2. Therefore, lines are parallel and distinct. Any questions?